Okay, so lecture 9 and lecture 10. Okay, so let me start off by saying that, well, I haven't done my homework, okay, and I haven't found the answers that Deva was looking for. So I'll be honest, straight up. So if I do figure that out, eventually I'll let you know. But there were some questions which were asked on Zulip by Deva Malya and Takato. So I think I've tried to answer them. Let me mention Deva Malya's question first. So he says in differential geometry, holonomy carries different significance from what Wilson line has. Holonomy is always associated with loop on the base manifold. So I think there was some misunderstanding about the terminology, because sometimes I was using the word Wilson line and sometimes I was using the word Wilson loop. So Wilson loop is just a Wilson line which is closed, right? I mean, it is a holonomy, right? Whether it's a closed loop or an open loop, it's a holonomy. If it's a closed loop and which does not enclose any curvature, then the holonomy is identity, otherwise it's non-trivial. As for topological degrees of freedom, they don't arise. You know, we have no need to discuss them as yet. These are all loops defined on topologically trivial background manifold. One can always ask what would happen if you introduced non-trivial topologies, right? And then we would have a different homotopy group for your manifold. And the other question that another possibility is that perhaps the existence of curvature itself could be interpreted as corresponding to some effective topological defects in the manifold. So that is again a possibility, but I will not talk much about that. Then Demalya had another question, which from earlier, which was that why does a puncture? He said he couldn't track the arguments when I talked about these punctures. So does a puncture create the singularity of a vector field? And I couldn't get why punctures are needed. Metric maps are V cross V to R, right, where V is a vector field. So how are punctures related to the metric? So in this case, I've explained on Zulip using the example of two observables which have compact support, and the way we define the commutator between such observables. So let's say that that you have two observables in your phi and pi, right? And using these observables, using these operators. So these are, well, they don't have to be operators. We can work with the classical phase space. So we define two observables, phi u, which looks like this, and phi v, which looks like this. Where u and v are some compact subsets of our spatial manifold. So you have the spatial manifold, and you have some region u and some region v, and these regions need not have any overlap. They can have overlap, or they don't need to have any overlap. So you can have a situation where they do have an overlap or where they don't have an overlap. Right. So if you calculate the Poisson bracket or the commutator between these observables, what do you get? You find that this is equal to, integral d cubed x fx d cubed x prime fx gx prime Poisson bracket of phi x and phi x. Right? And so this will give you integral of d cubed x fx gx, right? You'll get a delta function from this commutator for this Poisson bracket, and then one of the integrals goes away. Now here f has compact support on u. Okay, so f is a function which is defined on u, and likewise g has compact support only. It is compactly supported on v. All right, and that is why we can write phi of u and phi of v, right? Because we are using these test functions to smear out these operators or fields, right? So if u intersection v is the null set, right, then what will be this commutator? This commutator will be 0, right? Because when you do this integral will be 0. Wherever f is non-zero, g will be 0 and vice versa. Okay. Now, in the loop quantization, so in the classical space, there we have a connection and this co-triad, right? And so now we want to define in a similar sense, we want to define observables associated with this connection in co-triad. Now the connection is a one form, right? So if you want to smear this over some sort of a surface, what should you do? Well, there are different ways of smearing it. See, there is no algorithm which tells you that you should only do it in this way, in a certain way. I mean, you could, for instance, have some operator, I don't know, let's say a of u, right? Now this operator, for instance, if you smear a of I x in the same way, right? So now you have some test function and you're taking your connection and you're smearing it on some part of your manifold, some subset of your manifold, right? And your resulting of this thing, observable, has indices a and I, right? Now, the fact that a has an index, a spatial index, means that there is a natural way in which one can smear it, right? So this is one way of doing it, but another way of doing it is that instead of you smearing it over some three-dimensional surface, I take it, right? I take the one form and I integrate it along some one-dimensional curve, and then you would have dotted with NA, where NA is the tangent vector at each point to the curve. NA would be dxa by ds, where s is the the line element along the curve, right? So again, this is a choice. This is not like something which one could do this. One could proceed with the quantization and see if you get reasonable, if you can make sense of what you get, right? If you can make sense of the resulting state space, and if the constraints in the resulting formalism can be solved And if you can define operators which again have some which makes sense physically, right? I mean, we don't want to end up with just a formal quantum theory for the sake of it. We want something which gives us a background independent quantum theory of geometry. That is the goal here, right? So if to attain that goal, this choice is more natural than a choice of this form, right? And what will happen is, see, ultimately, if you did make this choice and you went through with the whole procedure, right? What you would find at the end of the day is that when you try to construct gauge invariant observables and operators, these functions f, right now they're just functions, arbitrary functions on your spatial manifold. What you would find is that again, when these functions become supported on the one-dimensional lines, right? So when they become zero everywhere except along one-dimensional lines, that is when you would get sensible answers, right? So I don't know if anybody has actually done that, followed through that program, just to show that this does turn out to be the case, right? But that would be my expectation. Okay. Similarly, for the co-triad, so this for the co-triad. Now the co-triad is a two form, right? So again, one can proceed with this kind of a construction, right? Smear it over some compact region V with respect to some connection, with respect to some test functions which are defined on that region, right? But now you are left with an object which has some indices. Now there is another problem with defining such observables. What is that problem? That problem is the fact that what are these indices? These indices refer to the tangent spaces at each point, right? But when you integrate over some subset of your manifold, right? That subset, in that subset, the tangent space at each point can change from point to point, right? Because your manifold is curved. So it is not clear in what sense would this index on this coarse grained observable, how this index would be related to an actual to some sort of a tangent plane, right? Because what you would be doing is you're averaging over all the tangent planes in that region, so to speak, right? So the connection, this one form at a given point is not trivially related to the one form at another point, right? Simply because when you go from one point to another point, what can happen is that because of curvature, because of the curve geometry, your frame can rotate, right? And if you are in a flat background, then yeah, it doesn't matter. Then you can use this. Then there is no issue. Fine, we can use it. It makes sense. The tangent plane is the same everywhere. The tangent space is the same, has the same. There's a trivial connection, right? So that is actually a better reason, apart from utility in terms of the ultimate utility. That is a better explanation, I think. So if you want to construct observables which are diffeomorphism invariant, right? So these observables would not be diffeomorphism invariant. So if you want to construct an observable which is diffeomorphism invariant, you have to smear it along surfaces Right. So that's, I guess, the long and short of the story. That those are if you want to construct diffeomorphism invariant observables, you have to do it like that. Similarly, for the co-triad, you would smear it along some subset V, but this subset V, dimension of V, right, would be it is some two-dimensional surface, right? And what is NA? NA X is the normal vector at each point on that surface. And yeah, you would have to like require the surface to be orientable, right? You would impose some obvious sort of requirement like that, because otherwise you can't have, you don't have a well-defined integral in this case. So once you define your observables in this way, right? And now you ask, well, what is the Poisson bracket between, let's say, A? So now what happens? This AU, well, it actually becomes A gamma, where gamma is a one-dimensional curve, right? So your gamma becomes your this subset U. And similarly, EV becomes a surface S. So V becomes your compact region S becomes some surface, some two-dimensional surface S. And now one can ask, well, what is the Poisson bracket between these observables, between this smeared connection and this smeared triad, right? And again, let us go back to the field theory example. When our subsets here, the subsets over which we have done the smearing, when these subsets don't overlap, what happens? Our Poisson bracket vanishes. Well, obviously, right? I mean, operators at space-like separations, they commute with each other. So this should be equal to 0 if gamma intersection S is equal to the null set, right? For the exact same reason that if these two sets don't intersect, these two regions don't intersect, then this commutator will be 0. So the key point you have to keep in mind is that in field theory, one doesn't work with operators defined at individual points, right? You have to work with smeared operators, smeared observables. Right? And so this is 0 unless the curve intersects with the surface. What does that mean? Well, this is a surface. This is some curve. There is no intersection. Poisson bracket is 0. But if there is an intersection, now we have a two-dimensional surface and a one-dimensional curve. What sort of intersection can happen? Well, this is a possible intersection, right? They can intersect at one point. Another possibility is that the curve could lie in the surface, along the surface, right? And then again, it could maybe exit like this. And then perhaps again come out, right? So what happens is that this Poisson bracket becomes non-zero only if there is some non-trivial overlap, which means there are some punctures. Right? We would say that the surface S is being punctured by the curve gamma. Okay. So that is where these punctures come from. Does this maybe help clarify things any? Devamalya, I don't know. Devamalya is.
It is being clear.
I don't know if I managed to dispel the clouds of confusion. Then, of course, there is this
So,
question regarding what, sorry.
no, it is now clear, and I have to study the Thiman book in detail.
Right. No, I think it's very like courageous of you as a postdoc who is not working in this area to actually be willing to learn this whole new formalism while at at the same time as you have to like sit and write papers to keep your to earn your academic credentials. So my hats off to you in that regard. So there is this other now this question which was asked by Takato also previously. What happens when the overlap or the intersection between gamma and S is such that the gamma section of or some subset of gamma lies along S, right? So there again, well, as I had given this sort of heuristic argument that well this region will not contribute to the Poisson bracket, but only these regions will contribute. Where the curve exits or enters or goes through the surface. These are the places where you will get a contribution. Okay, and again, why do we smear in this way? Because this is diff invariant and this is not diff invariant. So that's the one this would not respect the diffeomorphism invariance. Oh, sorry. This is not. Okay. All right. So now, then what else? All right. So are there any other? So yeah, and then they only asked a question, which was that how are these metrics? How do they capture how do these punctures capture the information that is encoded within the metric? Right, and that's a great question. So that is what I'll talk about today. So we'll be talking about the definition of something called the area operator. Okay, and hopefully that will again provide some more clarity. All right, so let me do that. Right, so now we want to talk about observables, right? Well, what sort of observables should one do? Like I said, again, we don't have any guidebook or any algorithm for determining what observables one should construct. Our guidebook is our intuition, right? And our intuition is that our intuition itself is molded by our what would you call it? Our goal, which is to construct a diffeomorphism invariant quantum theory, right, of geometry, right? Because that's what Einstein gravity is. It's a theory of geometry. It's a classical theory of geometry. So the quantum theory of Einstein gravity should also be a quantum theory of quantum geometry. So this is the what you would call our overarching agenda, I suppose. Okay. So now one of the observables that we can construct from that perspective is the area of a surface, right? Again, this is not obvious right away just by looking at this kind of a structure. This is something that is why the original works by Astiker, Rovelli, and Smolin are so momentous, right? Because they recognize that this sort of an operator can be constructed using these states. So you have some surface, right? And on this surface you have some metric HAB, right? And this is a two-dimensional metric, so I'll call it 2 HAB. And this 2 HAB arises from the restriction of the metric on the two-dimensional manifold. So this is defined on sigma, and then when you restrict it to S, you get HAB, right? So how should we calculate this? How should we calculate this area? Right. So what we do is we work with this triad formalism, and we say that at a given point P on our surface S, at this point we have a R triad, right? And we choose this triad in a way that one leg is normal to the surface and two legs lie within the surface, right? So one can always make a choice of this orthonormal triad at a point in P such that two of its legs span the tangent plane to some surface S, right? So these two legs, they become a dyad, right? And so we will label them like this: EAI, EBJ. Okay. So different color, just to distinguish these objects, right? And then again, since we have already used this, right? So let me use a different notation. Let me call this capital AB to distinguish from the ordinary three-dimensional spatial indices. So this 2 HAB can be written exactly in the same way as the contraction of these triad elements, right? So in terms of, if I write this out in matrix form, what do I get? Well, right, there I put some coordinates x and y on my surface, right? So in terms of those coordinates, this is what my matrix is. And in terms of this expression, if I write down the components explicitly, I get EXJ, EXI, EYJ. So when I was first working out this derivation of this area of operator for myself, I looked through many textbooks and papers, but nowhere could I find a decent and proper, complete derivation which showed me that the area operator does come from this co-triad in this way. And I happened to be working on this review paper on LQG, and so ultimately I had no choice. I had to sit down and work it out for myself, right? So what is this? So So this becomes, now we want this determinant of this 2HAB. Right?
Deepak, I had a quick question.
Yes.
It's about notation. You're calling these co-triads. Are they co-triads or are they co-dyads?
So right now I'm working with the normal with the triad. So this is the small e. This is the triad, not the dyad. Okay. Or should it be the? I mean. Yeah, no, because the way you define the metric, right? The way you define the metric, if you remember the definition of the for example, the 4-dimensional metric was like this, right? This was in terms of the triad, and similarly the definition of the 3-dimensional metric is also in terms of this triad. Now you can, instead of this, you can write the definition in terms of the densitized co-triad, right? But then what will happen is you will get a certain factor because which will have to take into account the fact that that co-triad is a density, right? So it has some factor of the determinant of that which is already present. So you have to divide that out. Okay. So right now I'm working with just this ordinary object. I mean not the co-triad. Okay. Is that okay?
No, I mean, what, for example, the E mu I, E nu J that you've written besides G mu nu, I thought they were called tetrads. The one to the right, I thought they were called triads, and now I thought we were going to talk about
no. These are tetrads. These are triads. This is a dyad, right?
Yep. Okay, perfect.
But the dyad will end up being given by this co-triad, right? This kind of, so when I work through these expressions, we'll end up with something in terms of this co-triad. So the co-triad again, let me just write it down. Co-triad 1/2 epsilon A B C epsilon I J K, A B C epsilon I J K, E B J E C K, right? So if you look at any two of these vectors, so if you for instance, so you have at a given point P, you have three of these vectors, let's say, right? So you have E1, E2, and E3, right? So we are looking at this. We are writing down the area of the surface by taking this cross product E1, E2, and that will end up, you can see that will correspond to the, if I put J and K to be 1 and 2, then I'll get I is equal to 3, A would correspond to 1/2, right? Epsilon A, B, C, epsilon 3, 1, 2, EB1, EC2. Right? In other words, this EA3 is equal to this vector E1 cross vector E2, 2, like this. Okay. All right. So, I mean, I'll continue, I guess. So if you look at this, the determinant of this matrix, right? That's what we need to calculate this, this quantity. So det H, right? So we can just read it off, right? X, 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 Y, X, Y, Y, X. Okay. And now let me write down the same expression in terms of this dyad. So what will I get? EXI, EXJ. And then I have to use a different, so then EXK, EXEYL, right? So I have to use a different index structure. So here IJ, so I have to put something like KL over here. So XX, sorry, so this will be YY minus EXI, EYJ, EXI, EYJ, and then EY, let's say K again, and EXL. All of this contracted with delta IJ and delta K. Okay. So Haridas sir said something, I think that was in response to your question. Okay. Now, here we'll use a little bit of this thing. We'll use a bit of a trick. Okay, that if you take epsilon IJM and you contract it with IJ. Okay, let me use my indices of capital IJK contracted with delta IJ. You get 0, right? And if you take 2 epsilon tensors, right, IJK, and you contract this in terms of IKLMN, let's say, you would get delta JM, delta KN, anti-symmetrized, and I think there's a factor of 3, I think. And then if you contract over 2 pairs of indices, so IJKL, you would get delta KL. You would get a single Kronecker delta. Okay. I forget what the factor is. So I'll just put a ball with some shading. I call this Ashtekar notation because I saw it when I attended his lectures, and whenever there was, so he was on a completely different level. Okay, I'm not saying that. So whenever he left out some constant, you could ask him what it was. He would give you an answer. In my case, that's not necessarily the case. But still, I have found this to be a very useful notation over the years. Okay. Right. So then this expression, using these identities, we can write it as well. When you do all this and you simplify everything, it becomes EMZ EZN. And again, sorry, I should use capital letters. I'm working with capital. Okay. So this is, and again, this is not surprising. This is just telling me that this third triad is given by the cross product of these two, right? And the area of that element is simply the norm of that vector. Okay, this is what we find in three-dimensional geometry, right? So we have U and V and W. W is equal to U cross V, right? And what is the area of this parallelogram? Area is U cross V, right? The directional area, and we represent it by this, by the cross product, which is this V. Okay. So we can write the classical expression for the area of this surface now as root of. So it's a complicated way to say something very simple. Okay. Now this E I can write in terms of the cotriad. Okay, because you know that we can invert the relationship between the cotriad and the triad, right? So where is it? Let me go back a little bit. What's the definition? Right. So I can invert this relationship to express to this triad in terms of this cotriad, right? So let me copy this and go all the way to the front. Okay, and paste it here. Right. So if I take this, let's say, and I contract this thing with epsilon something, let's say A dE and epsilon IKL, right? And then I would contract this epsilon with this epsilon, this epsilon with this epsilon, right? I would get a bunch of delta functions and so on. And that would give me, so let me write it down. I'll get delta D delta E, sorry, C D E delta J K and then delta J delta K delta B J E C K. All right. So when you go through all this, all the delta functions, you can get something like you get E D E D M E E something like that. Right? Okay. And now what? Now I think you would there would be another contraction with one more factor of the triad here, and then okay, there would be some more algebra, but the end result would be that let me just write down what the end result is. The end result would be that your area operator yes, give me 1 second. 1 second. Sorry for the interruption. Sorry for the interruption. My wife is actually not feeling so well today, so she cannot manage the little one, and so the little one will have her say. She's banging on my door even though I locked the door. So, and I apologize for this very unprofessional interruption. Beta. आपकी क्लास है, ठीक है। जाओ तुम यहाँ बैठ जाओ, बेड पे बैठ जाओ, बेटा क्लास पढ़ा रहा है। यहाँ पे बैठ जा प्लीज। अच्छा ठीक है, ओके ओके, थैंक यू। ओके सो पापा क्लास पढ़ा रहे प्लीज, ठीक है, पापा क्लास पढ़ा रहे। So let me write down what this area would be in terms of the co-triad. It can be written in a similar way as this integral over d to x square root of this let me try and just please I'm sorry, give me a second, I'll just pause the recording and try that. Okay, yeah, I would apologize for that, but what's the point? It's too late, right? No, I mean, kids are wonderful. Kids are the best thing ever. But so yeah, this can be written in terms of the co-triad in a similar way. So you have some EAI, EBJ, and then you do some contraction with delta IJ. Okay. So yeah, I'll leave it at this. So now the question is, how do you convert this into an operator? And moreover, how do you convert this into an operator which acts on these graph states? I mean, I haven't exactly shown it, but I hope that you can see why this should be the case. Right? I hope so. Okay. One way to see it is that if you look at this determinant H, right, it has 4 factors of this triad. And if you look at this co-triad, each co-triad has 2 components of the triad, right? So you get those 4 factors here. So now the question is, how do we construct this operator? So let us remind ourselves what our graph states look like. Some set of and your state psi function of the holonomy along. Keeping in mind the clarification that I had made in response to Takato's question in the previous lecture, that by edges we mean only those line segments which are connected to nodes with valence more than 2. So if you look at an edge of this form with where you subdivide a single edge by inserting a node, right? This doesn't count because here, you will not G2. Okay, now I take a given edge and I take that edge and divide it into two parts. And for one part, I assign the holonomy Gi, and for the other part, I assign the holonomy Gi prime, right? So this is for the ith edge, divided in this way. Now, because Gi times Gi prime will simply be the holonomy associated with that edge, right? This is just a property. So then this state would reduce to exactly what it was before you made this subdivision. Okay. And how do these operators act on such states? So let us ask what will be the quantum version of this operator. Okay. So again, proceeding in the naive way, let us how should this functional derivative act on our states? Okay. Well, first of all, let's look at the form of this operator. This operator involves a sum or an integral over some surface S, right? So in order to define this operator, this area operator, first of all, we need to specify that right. We are going to probe the geometry of our graph using this surface. All right. Now what we do is we immerse now, and so then we ask, well, what happens when I put this surface? When I use some particular surface, what happens? Well, what will happen is that maybe some of these edges will intersect the surface, and maybe some of the edges won't intersect the surface, right? As before. So let's say two of these edges intersect the surface. This is G1, G2, G3, and G4. Let's say the E3 and E4 intersect the surface and the other two don't, right? So when you evaluate this operator, first of all, you will only get a contribution from a non-zero contribution from these two punctures, right? Because well, this is not defined anywhere else, right? These operators are acting on this surface only, so nothing else is going to affect it. So how should we write down the quantum version of this operator? AS. We'll write it as sum over all the punctures. So P belongs to our gamma intersection S. Gamma intersection S means that all the points on the surface, the edge, we have a square root delta ij. Then we have some factors of h bar that I'm leaving out for now. We can put them back in later. And what does this become? This becomes delta az, delta a, ai, bj, and this whole thing. So there'd be delta ij, and there would also be a There will also be a delta AB. This whole thing. So we have A of S acting on psi gamma, acting on psi gamma. Like this would be your definition of the area of this area operator acting on a state. Now, how would this area operator act on this state? These derivatives, right? These derivatives would act only on the on those edges which have a puncture with the surface. And then one can ask, so what is the way? What is this state psi? It's a functional of these holonomies, right? So then one can ask, well, what is this? Let's say G1 to Gn, right? So this will give me a non-zero action, which will be given by something like this. Let's say psi delta Gi or delta G M, and then delta Gm delta A, like this. And then there would be a sum over all the holonomy, all the m's which belong to the punctures, wherever there is a puncture. So what we need to do is we need to evaluate the derivative of the holonomy with respect to the connection, the functional derivative of holonomy with respect to the connection. Now, what is the holonomy? Once again, path ordered exponential of, and I'll use a different index, bj tau j dx, like this. So this is the line element. I've just put the index on the line element to incorporate the tangent vector into this differential. So now one can ask, what is the functional derivative of this guy with respect to the connection? Okay. All right. So actually I should be a little bit more careful and keep the normal vector outside. Yeah, I'll do that. Keep the normal vector. Sorry, the tangent vector. This is the tangent vector. So when you take this derivative, what will happen? You will again, taking a derivative of an exponential, you will get the derivative of this integral, and the derivative of this integral, when you take the derivative of this a with this a, you will get a delta function. When you integrate that, you will get a non-zero contribution only from the puncture, and you will get a factor of, so it will look like this, minus I tau, and when you take into account all the various indices, tau a and I, defined at the puncture, and again you and one copy of this G of A. So this is we are just taking the derivative of this, okay, of the exponential. So if I want to write down the derivative of the whole state G1 to Gn, what would I get? I would get Na tau I at the location of the puncture times the state G1 to G. Okay, so now we can focus on a single puncture, on a single edge with a single puncture. This is your edge. Let me draw the tangent vector to this edge. This is the tangent vector to the edge at the surface. Okay. Okay, everybody still there? I hope. Got disconnected there in the middle. So when I put two operators, two functional derivatives, well, what will happen? What will happen is the following: delta AI, delta ABJ psi, right? And I will get two copies of my Lie algebra generators, two copies of my tangent vector. Once you get used to giving holding classes and giving lectures with this kind of software where you can just move equations and copy them and paste them, you never really want to go back to a blackboard ever again, right? Times psi. Okay. And then there is a contraction over this delta AB and delta IJ, right? So again, looking at what happens when I act on this state with this area operator, what will happen? Here I will get the norm of this tangent vector, right? And this norm is equal to 1. Right? We can take it to be equal to 1 by choosing a suitable parameterization of curve. Again, you have four functions, and so P belongs to gamma intersection S. These are a function. Not me. Zoom is really sorry about that. Again, I got disconnected. So what is this tau I? Remember that we are working with a certain gauge group, right? So what is your gauge group? Well, it's SU2, right? Or, you know, I mean, one can take it to be SO3, but for the time being, just take it to be SU2. And what are these generators? Well, these generators are simply the operators for angular momentum. Now the screen is not updating. So these are just the operators for angular momentum. And corresponding to each, the operators acting on each edge, the edge wherever there is a puncture. Okay. So now the question is, how should these operators act on this state psi? Right? And there is a very natural action. The action is simply given what are the eigenvalues of these J operators, right? What do you get here? You get tau square. And tau square is what? It's J square. And now J square acts on this edge, which carries some holonomy, right? But you remember that by the Peter-Weyl decomposition, we had written our function of G as a sum over this sum over the various group representations, right? Over all the possible J's and M's. So what happens when J square acts on this state? Well, you will get simply the eigenvalues of the J square operator. What are the eigenvalues of J square? J times J plus 1. Right? That's it. So what you have to do is you have to write this state in the spin network decomposition. When you write it in the spin network decomposition, the action of these Lie algebra generators on the edges will simply give you a factor of this angular momentum squared for each edge. So what will be the area associated with a single puncture? The area, well, if you take into account all the factors, 8 pi G Newton, and the imagery parameter, this is gamma is the imagery parameter, and so on and so forth. It's J times J plus 1. This is the eigenvalue of the area associated with a single puncture by an edge which carries a spin J label. Okay. Now the question becomes, how do you define the area of a surface which has many punctures? So if you have many punctures, first I'll tell you how it is done in the usual LQG literature. There what is done is, well, you just say that this is simply h phi G Newton gamma and all of this I think is just LP square. There are factors of h bar and c which are mysteriously appear as they always do in such expressions. And you have a sum over all the punctures. Let me label the punctures by some k, and the area is written as the sum over all of these over the sum of the areas associated with each puncture. So A1, A2 to AK. Right? This is the expression for the area that you will normally encounter in the LQG literature. Okay. But one could argue that this is not the right way to calculate the total area or the total eigenvalue of this operator, right? Instead, what one should be doing is that you should write down the area not as the sum of the square roots, but as the, right? So you should first define a total Casimir for the whole surface by summing over the Casimirs for each puncture, and then take this quantity. So if you do this, right, then what will you get? Because many particles with angular, you can't just, you have to look at the, if you want to calculate the total angle, this operator will give you sum over k, jk times jk plus 1. And well, no. And then finally, I would say that the area is given by this h by g Newton gamma, square root of this sum. And this in general would not be the same as the other area, right? This area, sum of the squares. Now, for instance, why this would might make a difference is that this is the expression that is used in the Rovelli's counting of black hole surface microstates. Okay, but the thing is that this kind of accounting is only valid if any entanglement between these different punctures, right? So if your state can be written as a product state of the quantum state defined at each puncture, right? It would be equivalent, right? Root of sum of jk squared would be equivalent to sum of root of jk squared. This would be equivalent if psi is a product state. But if psi is not a product state, right? So if psi is a product state, if psi restricted to the surface, psi surface is a product state, so it's J1 J2. Okay, no, even then it would not be true. So I guess I should. Anyways, so yeah, whether this will make a difference or not in the counting, I don't know. I've not actually worked it out. My guess is that it won't. It will make some difference maybe to the subleading order, but not to the leading order, because you would be considering, we consider the limit of large number of punctures, and in that limit, these two expressions would coincide. And so yeah, so this is the area operator. And one thing this area operator allows us to do, it allows us to count. We can count black hole horizon microstates. Right? How do we do that? Well, our black hole horizon is a two-dimensional surface, right? So we say our geometry is given by some graph, and the edges of this graph puncture our horizon surface. Wherever there's a puncture, we get one quantum of area. Right? And then the total area of the horizon, of the surface, is the sum of all the areas of the individual individual punctures. Let's say there are n such punctures, right? Now the thing is that each puncture has a different spin representation, J1, J2, so on till Jn. Right, so some punctures can carry spin 1/2, some punctures can carry spin 1, some could carry spin 25. Right. So now the thing is that, yeah, if we if you don't put any restriction on the spin values, right? So then what we have to do is we want to calculate the entropy associated with this. So this is our macro state, and this is our micro state. And what we want to do is we want to calculate the entropy associated with this macro state. So what would be the entropy? It would be equal to K log omega. What is omega? Omega is the number of punctures, number of ways in which you can puncture the surface S. Right? With such that the sum of areas of all punctures, right, of all the individual punctures, it lies in some interval, some small interval A and A plus delta A, where A is your macroscopic value of your horizon area. Right? And now if you do this counting, what you find is you find that, well, this area, this omega turns out to be so let's see. When you do this counting, what you find is that omega turns out to be proportional to exponent of the macroscopic area, the sum of overall the case. And so the entropy therefore becomes proportional to the area. So at least, I mean, to this extent, right, not including coefficients of factors of 1/4 and all that, to this extent, loop quantum gravity has given us the Bekenstein-Hawking formula, right, up to proportionality. In and of itself, this is a remarkable achievement. But there are many caveats. This corresponds to the entropy of a non-rotating, non-charged black hole. What happens if the black hole becomes, if the black hole has some rotation, and what happens if the black hole develops some charge? Okay, so those are two questions. Then you have other questions such as your choice of the total area operator, whether it will make any difference. And again, as I argued, that for a macroscopic black hole, it will not matter. Those two expressions will agree in the limit of large number of punctures. And what else? And yeah, and then there's of course the question of dynamics, right? So what is this? We are working with a we are working with a single spatial slice, right? And this is not the horizon strictly. This is the restriction of the horizon to a single spatial hypersurface, right? So in order to do this calculation in the proper manner, right, you have to actually use something called you have to work with something called the isolated horizon framework. You have to work with isolated horizon. An isolated horizon is a trapping surface, or a minimally trapped surface, which is defined by the criterion, so it's a minimally trapped null surface, which is defined by the criterion that so a null surface has two normals. One is an ingoing normal, let me call it U. Another is an outgoing normal V, or maybe Ni and No. And it is defined by the requirement that the expansion associated with the outgoing normal is 0. What is the expansion? The expansion is the trace of this trace of this object, the trace of the extrinsica which are associated with that normal. So this expansion tells you whether the surface is expanding or not, basically. Is there an upper bound of entropy, or is the area operator a bounded operator, right? So the area operator is not bounded, right? It's bounded from below. That's the most important thing, right? It has a minimum the smallest eigenvalue of the area operator is non-zero. That's the first thing. So that is very important, right? That means you cannot have an area smaller than you cannot have a size of any region of space-time which is smaller than that quantum. Okay, and that is completely in line with our expectations from any theory of quantum gravity, right? Whether you look at non-commutative geometry or string theory or whatever. Then is there any upper bound? Well, no, right? Because your graph can be as big as you like, and your spin labels can be as large as you want them to be. So there is no upper bound, for the same reason that, well, if you look at the volume of a system, that system can be arbitrarily large. So this is, and then there are other questions related to this area operator, which is that what if you consider entanglement between these functors? What if you think of this as a product state? What will happen in that case? And so I believe that in that case also you will get the same result, because, well, the total Casimir associated remains the same regardless of whether you have an entangled state or product state. Doesn't matter. Right. And this has a very nice the last week of December, a paper came out by Patrick Hayden and Jeffrey Pennington. So these are like Patrick Hayden is already quite well established as a one of the leading thinkers in this black holes and quantum information. And Jeffrey Pennington is like this rising meteor, more like a rising volcano or something. And so what they have shown is that if you look at if you consider something to do with the subadditivity of quantum channels. Okay, again, I don't know much about that, but if you consider the area operator as a quantum area of a surface as a quantum channel, and you believe the validity of something, the subadditivity conjecture or something like that, then that necessarily implies that the black hole microstates must be given by, there must be a set of unentangled states near the horizon which contribute to the black hole entropy, or to the majority of the black hole entropy. So I like that result because it is in sync with what we are getting here, right? These punctures, they are all, I mean, like I said, they could be entangled with each other, but because of the way in which we are calculating this operator, right? It's just taking the sum of the angular momenta of each puncture. So it is as if you were looking at a collection of unentangled spins living on this horizon. Right. So another piece of, I mean, evidence, I think, in favor of this loop quantum gravity system. So this is one very nice application, right? Another thing we can do with these quantum states is we can define a volume operator that I will define in the next session. So how many of you are interested in having one more session after today? Can you raise your Zoom hand? Today is the 10th lecture. How about Preetham and Takato? Are you guys interested in having a couple of more sessions? Okay, good, excellent. That is universal agreement. Nothing makes me happy than unanimous consent. Right. So we'll have another 2 sessions at least, and I'll talk about the volume operator, and then I'll talk about LQC, loop quantum cosmology. Right. And whenever I talk about these things, please, I also try to mention all the possible caveats there are and all the pitfalls and places where something might go wrong. And I don't take any of this as the ultimate truth. And Dev Malya is asking to talk more about entanglement of punctures. And well, I'll try to talk about that in the next session on Monday. Okay. And then I want to also conclude by talking about the relationship between spin networks and all of this tensor network nonsense that has been going around, masquerading as something different from spin networks. I mean, it's not nonsense; it's good, solid science. But it's as if, you know, you have Maxwell's theory and you have somebody else, and they're calling their theory by a different name and selling it to the whole world. So justifiably, Maxwell would feel a little peeved at that fact, especially if Maxwell doesn't get those nice jobs and those nice grants. Okay. But it's understandable because, well, whatever, the sociology, blah blah blah. I take hope from this one saying that Barack Obama likes to use all the time, that the arc of history is long, but it always tends towards justice. Right? So, I mean, that's like one of those bullshit sayings that politicians always use because it's like, how long is the arc of history and how much does it bend? It doesn't matter. Those are variables, right? So it could arc could be centuries long, and the bending could be like, this much or this much, whatever. It'll be enough to cover up for all the other logical inconsistencies in their approach. And the other saying is by, I forget whom, by Planck, I believe by Planck, that he said that scientific revolutions do not happen because one group of people succeeds in convincing the scientific community of the correctness of their approach. Rather, they occur when the believers of the old approach gradually become old and die. This I believe is what Planck said, and this is true. And time is our best ally in that regard. I mean, I wish long and happy lives for all the great string theorists on this planet. I definitely don't wish them any ill will. Anyways, on that merry note, wish all of you a very happy new year. And yeah, so all I will say is that even if you don't care about loop quantum gravity, do study tensor networks, because if you do, then I will take comfort in the fact that you are secretly doing loop quantum gravity only. And also your job prospects will go up if you study tensor networks. All right. All right.
Can I? Yeah, I have two questions.
Yes. So.
Well, first, I'm not sure how the horizon notion appear as a choice of S.
Hello.
So,
sorry, Takato, your voice is breaking up a little bit.
Oh, really? Well, can you hear me? Can you hear me?
Yeah, now I can, yeah.
Okay, so in principle, you can choose any surface S and pick up
that's right.
The number of punctures, and this will contribute to the entropy.
Absolutely. Yeah, absolutely. Yeah.
So it's important to properly choose the surface so that and the entropy gives a correct Bekenstein-Hawking entropy. And
no, you're absolutely right, and that's why I mentioned this isolated horizon framework. And what this does is it gives us a boundary condition for the surface that becomes our that corresponds to our horizon surface, and that boundary condition puts a constraint which relates the curvature of the connection on that surface, right? So you have some connection in the three-dimensional bulk, right? So now I'm talking at the level of the classical theory. And then if you have any surface, you can take the pullback of that connection to restriction of that connection to the surface. And similarly, one has the co-triad, which is defined in the bulk, and one can look at the co-triad, which is defined on the surface. And what you find is that there is a relationship between these two. And so this constraint is what is used to identify what we refer to as a isolated horizon or a black hole horizon. And so I'll go into this in a little more detail next time. I think I'll have to talk a little bit more about this trapping. What we find is that Chern-Simons theory makes another appearance here. And whether this may or may not contribute to answering your questions regarding asymptotic symmetry and soft modes. So as far as I know, nobody has really looked at that in this connection picture, but I think it's a very good topic. It's a very important topic for research.
Well,
yeah.
Well, does the boundary condition, does the similar boundary condition applies for the matter collapsing case? So in case of collapsing matter creates some black hole, then the entropy should, the matter entropy should contribute to the final black hole entropy.
So again, right. So again, that is one of the big problems with LQG, right? Is that we don't have a proper understanding of how to talk about matter.
Mm-hmm.
So matter is always inserted by hand. No, I believe that, but I am in a very small minority, that I believe that matter already exists in the form of topological defects in spin network states. But as to the question of how you should talk about the matter entropy along with the geometrical entropy, I don't know. That's a question I've not thought about actually.
Mm-hmm. Okay. And my second question is the definition of entropy. Your definition is based on the Boltzmann entropy. But I was a little bit puzzled because when you consider some quantum states, it is rather natural to choose von Neumann entropy as a definition of entropy, because Boltzmann entropy assumes that all the distributions are uniform. And so why?
So what? So what happens?
Yeah.
What happens is that you can factorize your Hilbert space into a volume space and a bulk, into a volume part and a surface part. And then when you're calculating this entropy, I believe it turns out to correspond precisely to the entanglement entropy between the degrees of freedom which live on either side of the horizon. Okay, so it does correspond to the. So if you define if you think of this is your space time, and there are two regions, one is inside and one is outside the black hole, right? And then you define your density matrix for this system, and reduced density matrix, right? In the usual way, you trace over all the degrees of freedom within the black hole. Right. So and then you say that, well, what is the entropy, the entanglement entropy? Right? It's minus log minus trace of rho. This I believe it coincides with that, but again, I'm not going to make that. Say that for certain. The way I see it is that tracing over these degrees of freedom is equivalent to fixing the state on the boundary, right? Because when we fix when we specify this configuration of punctures, we are not saying anything about what is happening inside. What is happening on the graph inside the state. So in restricting our attention to the configuration of punctures, we are effectively summing over or tracing over all the degrees of freedom which are inside, right? And yeah.
So do you mean when we consider black hole entropy, we are implicitly taking some average?
I mean, yeah. I mean, we are tracing over the degrees of freedom, right? Inside, in the interior. Yeah. So I guess in that sense, yeah, we just take in over all the possible internal microstates.
I see. Okay, thanks.
Yeah. Okay. Any other questions? Any questions from my talented student Devadarshini, who has not asked a single question in this whole thing, whole enterprise?
Hi, sir. I actually haven't had time to study it, so no questions
No,
yet.
I know. You're working very hard in other things. Just giving you some trouble. Preetham, any questions from your side?
Yes, this last equation, I mean this constraint on this isolated horizon, this curvature is equal to this cotriad. I think this is not true for rotating horizon, right?
Right.
And
so
that
like
is the problem. That is the main problem.
Right. That's why I said that this only works for non-rotating black holes. Yeah.
So, sir, is there any progress in this in that direction? So.
Yeah, well, some progress is there. Some work has been done by Hanno Salman and his students, I think.
Okay.
Yeah.
Okay.
I think it actually is quite straightforward to look at the case of a rotating horizon by simply saying that this closure constraint, there's this closure constraint, right?
Yeah.
By simply saying that this closure constraint should not be zero. Because the closure constraint is simply saying that the sum of all your magnetic quantum numbers is zero. So what is the sum of all the magnetic quantum numbers? It measures the total rotation of your surface. Right? So that should not be zero. And if that is not zero, then geometrically it corresponds to opening up a deficit angle on the surface of this horizon. And that deficit angle would depend on depend on the amount of rotation. So the greater the rotation, the greater that deficit angle. So if you apply that closure constraint to a single tetrahedron, for example, it says that the faces of the tetrahedron close. But if you say that the closure constraint isn't valid, then you have an open tetrahedron.
Okay.
And how open it is, it depends on how fast it's spinning. So, but again, this is something I've like thought about, but I haven't worked out the details.
Oh, thanks.
Okay. All right. So I will see you all on Monday. And again, thank you all for coming, and I wish you all a very happy New Year. And best wishes to all of you.
Happy New Year, sir.
And your loved ones. Yeah. Okay. Bye.